Okay, so we're happy to have Zhilin Luo from the University of Minnesota, who will talk about the stable transfer for sim and lifting of GL2, the Archimedean case. Give me just one moment. Okay, go ahead, Zhilin.
Okay, so thank you for the introduction, and the title of my talk is on the stable transfer for sim and lifting of GL2, the Archimedean case. Okay, so let's first briefly recall something from the local class field theory. Let's fix F a local field of characteristic 0, and we let WF to be the weight group of F. Then the local class field theory says that there's a canonical continuous group homomorphism from the weight group to F cross, which induces a topological isomorphism between the abelianization of the weight group with F cross. And in particular, the F cross can be identified with the GL1 of F. Then Langlands generalized the local class field theory, make his local length reciprocity conjecture to general connected reductive algebraic groups G. For instance, you can take G to be GLN, the invertible n times n matrix. And he also introduced the notion of L groups of G. When G is GLN, then the L group is just GLNC cross the weight group. Then you need to introduce the notion of the weight Zhilin group, clearly WF, which is just the weight group of F when F is Archimedean, and its weight group cross SL2C if F is p-adic. Then there are two sides of the correspondence there. On the one side, you have the local Langlands parameters, which consists of equivalence classes of admissible homomorphisms from the weight Zhilin group to LG. On the other hand, you have the irreducible admissible representations of GF. Then, for instance, when G is GLN, then the local Langlands reciprocity says that there's a unique bijection between the Langlands parameters of GLN and the irreducible admissible representations of GLN, which should be compatible with the local class field theory and the L functions and epsilon factors. And right now, the local Langlands reciprocity for GL is a theorem. When F is p-adic, it's proved by Hersh-Taylor, Hinya, and shows independently. And when F is Archimedean, it follows from the work of Langlands on the classification of irreducible admissible representations for more general reductive Lie groups. In general, the Langlands parameters give a partition of the set of irreducible admissible representations of G. For any parameter, you can associate to it a finite subset of the irreducible admissible representations of G, which is usually called the L packet. And in particular for GL, the L packets are always singleton. Then suppose you have two connected reductive algebraic groups H and G, and you are given a homomorphism, also an L homomorphism between their L groups. Then based on the local Langlands reciprocity conjecture, you have the following local Langlands functoriality conjecture for the morphism rho there. In particular, for any L packet, capital pi phi of HF associated to some parameter phi of H, then if you do composition with the morphism rho there, you can get the L packet of G that lifts the capital phi along the morphism rho, okay? Then on the other hand, for any irreducible admissible representation pi of G, there's an important invariant associated to it called the distribution character. By Hersh-Chandler, we know that the distribution character is given by a locally integrable functions on GF, which is smooth and even analytic when F is Archimedean on the regular semi-simple locus of G. And moreover, for non-isomorphic irreducible admissible representations, you can show that their distribution characters are actually linearly independent. Then here's a natural question. Langlands asked the following question in his 2013 paper. Suppose you have an L morphism between two L groups, then does there exist a stable distribution? I'm not gonna explain what the stable means, but you can just understand that roughly speaking, two elements are stably conjugate if they are conjugate over the algebraic closure. Then does there exist a stable distribution, which we denote by theta rho on HF cross GF, or more precisely, they are Sternberg-Hitchin basis, such that for any temporal L packet, capital phi, you have the following identity as locally integrable distributions. You integrate the distribution theta rho against the trace of capital phi h, then you get the trace of capital rho composed with phi g. Here, let me briefly explain the notations appearing in the equality here. So capital phi, the L packet is called tempered if the parameter has bounded image. And it is expected and proved in many cases that in general, the irreducible admissible representations in the temporal L packet are all temporal representations. And the trace of capital pi phi here is just sum over the character distributions in the L packet. And in general, we expect that the trace of capital phi is a stable distribution on HF. Okay. Then let's recall some known results before. So when F is p-adic and H is an elliptic torus in SL2, and the rho is the standard embedding from LH to LG, then the pioneer work of Gelfand, Grave, and Piatezzi-Shapiro shows that the distribution has an extremely simple and elegant formula. It's just 2 times the sign character of E. Here, E is the quadratic extension associated to the elliptic torus H. And the sign character is the quadratic character of F cross obtained via the class field theory. And here's trace G minus trace H over the absolute value of trace G minus trace H. Okay. And for the analytical issues involved, in particular, when the residual characteristic of F is not equal to 2, then Langlands himself also analyzed the question when H is a maximal torus in SL2, and the rho is the standard embedding from LH to LG. And the result of Gelfand, Grave, and Piatezzi-Shapiro was generalized by Daniel Johnston in his PhD thesis for H, an unramified elliptic torus in SLL. Under mild assumptions on the residual characteristic of F and the character formulas for the associated supercuspidal representations of SLL. Here, L is assumed to be a prime number. Then for all the known cases, the group H there is abelian. So here's a natural question. What about the case when both H and G here are both non-abelian? Then let's focus on the case when H is GL2 and the G is GLn plus 1. Then the L group of H and G are just GL2C and the GLn plus 1C, of course, cross the Wei group. And you take rho to be the symmetric nth power lifting from LH to LG. Then let's briefly recall that the local Langlands reciprocity for GL is known. Therefore, the functoriality from H to G along the morphism rho is known. And the L packets for GL are always singleton, and the stability issue for GL is equivalent to the conjugation invariance. Moreover, the classification of temporal representations for GL is known. Over the p-adic field is classified by Jacquet, and over the Archimedean local field is constructed by Knapp and Zuckerman. Okay, then let's first introduce some notations. We let Tn to be the diagonal split torus in GLN and Bn to be the upper triangular Borel subgroup. And we let Mn to be the Levy subgroup of GLN corresponding to partitions GL2, 2, 2, 2, 2, 2. In other words, you put diagonal GL2, 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 n over 2 copies if n is even, okay. If n is odd, then you consider the Levy corresponding to partition 2, 2, 2, 2, 1, okay. And the Pn is the parabolic subgroup of GLN that is upper triangular. Yeah, we always take the upper triangular parabolic subgroup here. And then we let DGLN to be the usual Y discriminant, okay. Then let's first see the case when F is equal to C, okay. Then in this case, by the classification of temporal representations of GL2, you know that the temporal representations of GL2C are all temporal principal series. In other words, it's just a full induction from the Borel to GL2. Here, chi1, chi2 are two unitary characters of C cross. And you can do some simple calculations and find that the lifting of pi around rho is just given by the full induction from the Bn plus 1, the Borel inside GLn plus 1 to GLn plus 1 of characters chi1 n and the chi2 to the power n minus 1, chi2 to chi2 to the nth power. Okay, you can do some simple calculations and you can very easily verify this fact. Then using the explicit character formulas for principal series representations, then you can find that indeed we can write down the formula for the distribution theta rho, which is just some delta distribution actually. More precisely, you define the theta rho as a parabolic induction of theta rho t, from which is a distribution on Tn plus 1c cross T2c to Tn plus 1c cross G2c. Okay. Here, suppose you have an invariant distribution on the Levy, you can always do parabolic induction to get an invariant distribution on the whole group. Okay. And then also you can write down the explicit formulas for this distribution. Here, theta rho t is supported on the regular semi-simple points of Tn plus 1 cross T2, which is given by some just the tensor product of two delta distributions. Okay. And furthermore, you can quite easily, just by some direct computation, you can find that if you normalize the character by the discriminant, then indeed this distribution gives you the desired lifting for character distribution for any temporal representations pi of GL2C. Okay, in particular for any temporal principal series. Then let's look at the case when F is equal to R. Then there are two classes of temporal representations. One is the temporal principal series, just the same as the complex case. It's a full induction from the Borel to GL2 of two unitary characters of R cross. Or you have the discrete series parameterized by LT. Here L is a positive integer and T is an imaginary number. Okay. Here's an issue. Previously, we constructed a distribution which gives you the lifting of distribution characters for principal series. But it does not work for discrete series because you know that discrete series has characters supported on the elliptic elements in GL2R. So here's a natural question, how to unify the temporal principal series and the discrete series. Then we make the following observation. We let omega pi to be the central character of pi. Then through computing the Langlands parameters directly, you can find that the lifting rho pi for any temporal representation rho is always of the form that is full induction from the parabolic subgroup Pn plus 1 to Gln plus 1 of a representation pi m plus 1 on the Levy. Here, pi m plus 1 is tensor product of pi 2k, k from 1 to n over 2, with the n over 2's power of the central character if n is even. And if n is odd, it's just tensor product k from 1 to n plus 1 over 2 of pi 2k minus 1, if pi is the principal series. Here, let me mention that pi m is just, you raise the parameter chi1 and chi2 to m's power, okay. And the omega pi, you raise the central character to power n minus m over 2. And if pi is a discrete series, it turns out that you have the same phenomenon as the principal series situation. You also, here pi m for discrete series is also the central character to the power n minus m over 2. And tensor with the discrete series associated to the parameter d of mk, mt, it should be mk mt, yes, mk mt. So basically, here pi m here is always we raise the central character to the power n minus m over 2. Tensor, you raise the parameter for the associated representation to the power m here. Okay. Therefore, by the character formula for the induced representations, you only need to determine a distribution theta of m plus 1 on the Levy cross GL2F, which yields a lifting of distribution characters from pi to pi of m plus 1. Then, moreover, we have the following character relation between the character of pi m. More precisely, for a temporal principal series of GL2, then if you raise the parameter chi1 and chi2 to the case power, then the character distribution is equal to you raise to the case power to the element gamma there for the original representation pi, okay, for any integer k. On the other hand, for the discrete series representation of GL2R, then similarly, if you raise case power to your representation, I mean, you raise the parameter to the case power, then as a distribution, it's equal to the original pi raised case power to the element gamma there. Here, we need to assume that k is odd. If k is even, then the left-hand side might be non-zero, but the left-hand side might be 0. So you cannot get the identity. Therefore, we can obtain the following reduction formula. When it's odd, let's assume that the distribution theta of diagonal n plus 1 over 2 exists, where diagonal n plus 1 over 2 is the diagonal embedding from GL2C to the L group of the Levy, okay, which is n plus 1 over 2 copies of GL2C. Then from the character relation between pi m and pi, you can obtain the distribution theta of n plus 1 from the theta of that diagonal n plus 1 over 2, okay. You simply raise the power g1, g2 until g n plus 1 over 2 to power 1, 3, blah, 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 until n minus 2 and n. And you put some determinant factor in front because you have some central characters there, okay. Then you can very easily verify that indeed this distribution gives you the desired character lifting from pi to pi of m plus 1 for any temporal representation pi of GL2 when f is Archimedean, okay. Then you can simply define theta rho as the parabolic induction of theta of m plus 1 from m plus 1 cross GL2 to GLn plus 1 cross GL2, okay. And the upshot here is that the functoriality for the diagonal embedding is just given by you lift pi to tensor n plus 1 over 2 copies of pi to the Levy, which is much easier than the symmetric nth power. However, it's still in progress to prove the existence of the distribution associated to the diagonal embedding, which seems to be not very easy from an analytical point of view. Finally, let's talk about the case. There are also some partial results for the p-adic case. Let's focus on the case when the residual characteristic of f is not equal to 2. Then the temporal representations, there are 3 classes. You have temporal principal series as usual. You have the twisted Steinberg representations with unitary central character, and you have the supercuspid representations with unitary central character as well. Then the story for temporal principal series is the same as before. And let's focus on the supercuspid representations, okay. Then by the work of Roger Hall, we know that the supercuspid representations of GL2 can be parametrized by admissible pairs. Here, E is a terminally ramified quadratic extension of F, and the theta is an admissible character of F, E cross. And for each admissible pair, you can associate to it a supercuspid representation, we denote it by pi theta, okay. Then, through computing the factorial lifting of pi theta, you find that luckily, the factorial lifting also has the same behavior like the real case, okay. It's also of the form induction from Pn plus 1 to Jn plus 1 of pi of Mn plus 1. And here pi m is also central character twist by n minus m over 2. Tensor, you raise the parameter to the m's power, okay. here, let me mention that the parameter, if you raise the parameter to the mth power, then the representation might not be supercuspidal. Okay. Then similar to the Archimedean case, we also obtain the following character relation between the distribution character of pi theta k and pi theta. Whenever you assume that k is co-prime to q minus 1 times q plus 1, where q is the cardinality of the residual field of f, then if you raise the power, if you raise the parameter to the k's power for your representation, then as a distribution, you also, it's also equal to the original representation. You simply raise k's power to your character. And in particular, we find that undermined assumptions on k and q, except the two-system representations, the distribution characters of temporal representations over any local field with the residual characteristic not equal to 2 really behave like the characters for abelian groups. And it seems that it admits generalizations to more general groups. Okay, my talk is over. Thank you. Yeah, thank you for listening.
All right, so let's thank the speaker by writing clap in the chat or clapping in the privacy of your own home. And if there are any questions, feel free to post them in the Q&A or raise your hand and I will unmute you. So maybe we'll wait for a few more moments.
Zhilin, could you repeat your result in the Peade case? What is?
Yeah. Yeah, you need to assume that k is co-prime to q minus 1 times q plus 1.
So what does this mean for the functions, for the kernel functions, for the I don't remember how you call them, the transfer functions?
Over the Peade field, unfortunately, we cannot say much because, for instance, we cannot unify the two-system representations, and when k and q are not in, if they do not satisfy this assumption, then basically you cannot reduce the construction to the diagonal embedding like the real case. In the real case, in the real case, we can really reduce the construction of the symmetric nth power lifting functoriality from GL2 to GN plus 1 using we reduce the construction to the diagonal embedding lifting, which is much easier than rho. But over the Peade field, we haven't got a satisfactory answer yet.
Mm-hmm. Thank you.
Yeah.
So I have a very silly question. Your very last remark.
Say again.
Your very last remark on the last slide.
Yeah.
That characters behave, that distribution characters behave like linear characters. Is that just an informal statement of the result above, or is there something more to that?
Yeah. Our point is that somehow we just observed that if you raise power of your parameter, at priori, it's not very obvious that it's just equal to the original character of pi theta. You simply raise k's power to an element. But it turns out that through the complicated computation and the character table from the thesis of Debaka, we verify this identity. Yeah, we don't know
absolutely. It's clearly an interesting result. What I mean is the result you've highlighted there and the remark, are those saying the same things, or is the remark saying something more or different?
I see. Yeah, it's just an informal statement, actually. It's just an informal statement.
Okay. Thank you.
Yeah.
Any further questions? Okay, so let's thank the speaker again, and then we'll have a few more announcements after. So.
Okay.